Welcome back to Physics 371 Online. We're going to continue with the separation of variables theme as an important method for solving Laplace's equation, and indeed for solving many partial differential equations. But now we'll look at a problem in spherical coordinates. And the cool thing about this is when we use a method to solve problems in spherical and cylindrical coordinates, we get similar kinds of results from our Cartesian coordinate example, but we learn some new mathematics. There are some new special functions that get defined because they turn up as solutions to some of the equations in spherical and cylindrical coordinates. So right here I'm going to focus on the spherical geometry. Very often, a problem like this can be simplified because it has a boundary condition with what's called azimuthal symmetry. Remember that phi is the azimuthal angle. So if we have a solution to the potential from Laplace's equation that doesn't depend on phi, in other words, where we can rotate about the z-axis and not change anything about the physical situation, then the solution is simpler, because it then only depends on r and theta, and there's no phi dependence. In this kind of problem, the general form of Laplace's equation, which, if you look inside your textbook, you can see that del squared v equals 0, and in spherical coordinates you have this rather messy looking expression. But if there's no phi dependence to v, then the entire last term drops out, and we get the simpler version given below. Now, we're going once again to look for solutions to the electric potential that are separable in the two remaining variables r and theta. And so we'll just say that there's a product of two functions, each of which only depends on one variable, r of r and capital Theta of theta. That may look a little strange, but that's a similar notation to what Griffiths uses in the textbook, so I'll stick with it. When we substitute this expression, this product solution, into Laplace's equation, we get this here. And one thing that we notice in both of these two terms on the left-hand side is that there's a 1 over r squared. So when we first, here it is, when we first substitute in the product solution into Laplace's equation, we get this form here. All right, we've basically realized that when we take the derivative of v with respect to r, only the capital R function is affected by that. So there's the derivative of r with respect to little r, and the theta function comes outside. The same kind of thing happens for the r function, the radial function, in the second term, because it only has a derivative with respect to theta. So now we see this 1 over r squared term in both terms on the left-hand side. So we multiply through by r squared, and we want to divide through by the same product function that we just substituted in a minute ago, because when we do that, it will give us the separable form to the solution. So we multiply through by r squared over capital R theta, and we get this. You'll see that we have one term on the left-hand side which is only dependent on the radial variable r, and then a term on the right-hand side which only depends on the variable theta. And there's a little mistake here. It should not say equals 0. We simply have these two terms equal and opposite to each other. Okay? Now, the same kind of reasoning that we used with Cartesian coordinates applies here as well. The only way for an equation like this to hold true for all values of r and theta is if both of the two terms are constants. That's the only way it can happen. And so, as a result, we end up with two ordinary differential equations. So the term on the left-hand side will be equal to one constant, and the term on the right-hand side will be equal to that same constant with the minus sign. So here is the radial equation, which is the term on the left equals to a constant c1, and the same thing holds true for the term on the right. This term is equal to a minus c1. Now, that equation, of course, because theta is the polar angle, is called the polar equation. There's something very special about these constants, c1, that appear in the spherical coordinate problem when we solve Laplace's equation. It turns out that the only way we can get solutions to the theta equation is when that constant C1 is the product of two successive non-negative integers. So that just emerges from the solution. So we usually write the equations like this. We take that radial equation, and instead of equals C1, we write it as L times L plus 1, where L is a non-negative integer. L equals 0, 1, 2, 3, and so on. The same kind of thing, well, holds true with the polar equation. We set that equal to minus L times L plus 1. So when we simply multiply through and do a little bit of rearranging, we have these two equations left. One of them now is the ordinary differential equation involving r. The other is an ordinary differential equation involving theta. And I didn't mention it, but while I was going through the derivation, at some point I dropped the partial derivative notation and replaced it with ordinary derivatives because of the separable nature of the solution. Capital R is only a function of little r. Capital theta is only a function of little theta. So we've done the thing we did before in Cartesian coordinates. By using a separable solution, we've transformed a partial differential equation into two ordinary differential equations. Now the solutions are not so obvious, but they can be solved. We're not going to derive the solutions here, but the solution for the radial equation looks like this. It is the linear combination, or the sum, of two terms that each deal with powers of r, to integer powers. The first term is r to the l. The second term has a 1 over r to the l plus 1 in it. So these two are power law solutions, or polynomial solutions. One of them increases as the radial variable increases. The other one decreases as the radial variable increases. And that'll become important in just a minute. Now, there's also a solution to the polar equation involving theta, and the notation that we use for this is that capital theta of theta is equal to P sub L of cos theta. Now, P sub L is the symbol that we use for a special function that's called a Legendre polynomial, and the L indicates the order. So P sub L of cos theta is the Lth order Legendre polynomial. It's important here that L has to be a non-negative integer, or else P sub L of cos theta diverges at theta equals 0 and theta equals pi. This is one of the reasons that we had to have L be a non-negative integer, so that these solutions would not have these annoying singularities at values of theta that we run into all the time, the poles of the problem. So there is a generating expression for the Legendre polynomial here, and you can use this if you want to calculate the 0th order, the 1st order, the 2nd order, the 3rd order Legendre polynomials, and I think one of these is assigned as practice for homework. One comment about this expression is that the d by dx to the lth power, what that means is take the lth derivative of the function on the right with respect to x. So if L is equal to 1, we just have d by dx. If L is equal to 2, we have d squared by dx squared. If L is equal to 3, then it's a 3rd derivative, and so on. And I see one more time that I've made a slight mistake in this expression. The L off here on the right-hand side should be a power. So this term should be x squared minus 1 quantity to the lth power. All right, so we now have solutions to Laplace's equation with azimuthal symmetry. However, you might be thinking, hold on, you showed me solutions to the radial equation, and since it's a 2nd order equation, there were 2 solutions. We're used to seeing that sort of thing. But in the theta equation, you only told us about 1 solution. So hold on. Why doesn't the polar equation have another solution? The radial equation does. So what's going on? And it turns out that there is a family of second solutions for the polar equation, but they are almost always unacceptable physically because they diverge at the poles, at theta equals 0 and or theta equals pi. So we're not going to worry about them, because if we introduce them, we would always just end up dropping them out because they won't match physically meaningful boundary conditions. All right, so that's where that comes from. So for azimuthal symmetry then, the general separable solution that is useful for physics applications is the product of the radial solution, capital R of R, and then the Legendre polynomial, which was the theta of theta. And so we will call this V of R and theta, and we'll label it with an L because, of course, L can be 0, 1, 2, 3, and so on. We get a whole family of solutions like this. And in order to match the boundary condition of typical physics problems, we will once again have to use an infinite series of these solutions. We'll have to have a sum over all the possible values of the order L, and then use that as the most general kind of solution that we can use to match the boundaries. So there's our solution to this kind of equation, Laplace's equation, in spherical coordinates, but we really need to see an example to know how to use this. How do we carry out this boundary value problem solution? So here's an example. In a charge-free region of space, the potential on a spherical surface that has radius r is some function v0 of theta. Maybe it's sine theta, maybe it's cosine theta, maybe it's some crazy combination of functions involving theta. For now, we'll just leave it as something arbitrary. All right, so our job is to find expressions for the electric potential V as a function of r and theta inside and outside the sphere. And I didn't say so, but this is going to be a problem involving azimuthal symmetry because it's a sphere and because the potential that's given on the surface of the sphere does not depend on phi. All right, so right away that tells us azimuthal symmetry is in place. So here's a diagram. We've got a sphere of radius capital R. We know what the potential is on the boundary. And so our job is to find expressions for the electric potential inside the sphere and outside the sphere. So what do we do? First, we establish the boundary conditions. We write them down because we'll have to use them to determine the constants that are in the general solution. So in this case, there are three boundary conditions. There's one that happens at the origin, and that's the bottom one here. In order for this to be a physically meaningful solution, V, the potential, has to be finite at the origin. All right, and so we can't have any singularities at the origin. V can't blow up there, and that'll become important in a minute. Then there's the other extreme. What about as we go infinitely far away from the sphere? And so just as we used back in the example problem for solving Laplace's equation in rectangular coordinates, then we can say that the electric potential has to go to 0 as r goes to infinity. All right, that's important because if r didn't tail off towards 0, it would somehow imply that there was charge permeating all of space, and physically that doesn't make sense. So the final boundary condition is the one that was actually stated in the problem. On the surface of the sphere, we know some function of theta that describes the electric potential values. So here's our general solution from the previous slide. What we need to do is apply these boundary conditions one by one, use this solution, and figure out information about these constants, a sub L and b sub L. So first of all, let's look at the boundary condition at the origin. The radial solution that's in parentheses here has two terms. As r goes to 0, the first term would be just 0 to the nth power. Okay, so it would go to 0. That's okay. It doesn't blow up. But the second term, if r goes to 0, we would have 0 to a certain power in the denominator. So this second term would go toward infinity. And that physically is not meaningful. It doesn't satisfy the boundary condition that V be finite at the origin. And so we have to simply eliminate the second term in the sum when we write down an expression for the electric potential inside the sphere. So for little r less than big R, we know that b sub L equals 0. And as a result, V in is equal to this infinite sum, but now the b sub L terms are 0, and it simplifies the expression. Okay, we can do now something similar outside the sphere as we go off toward r equals infinity. because once again, look at the radial terms. The radial solution has a term that gets larger as r gets larger, and then it's got a term that gets smaller as r gets larger. So since the potential has to go to 0, we also know that the first term in the parentheses has to go to 0 as r goes to infinity. A has to be 0, or else the overall electric potential will not tail off towards 0. So for little r greater than big R, the A sub L term is 0, and that gives an expression for V out that involves just the B terms and not the A terms. So these two forms, V in and V out, are very important. Our job now is simply figure out the values of the A sub L and the B sub L coefficients that allow these two expressions to match the boundary, okay? To match the place at r equals the radius where these two are supposed to be the same. So, how does this work? Well, let's take the inside solution, plug in little r equals big R, and set it equal to the function that we know represents the potential on the surface. Right? So V in of big R and theta, well, we take the expression for V in from the previous slide, plug in little r equals big R, and then set this equal to the function V naught of theta. All right, so now what's left for us is to dig out the values of A sub L that make this equation true. How do we do it? Legendre polynomials in some ways are just like sine functions and cosine functions. They're orthogonal to each other. So we're going to rely on this orthogonality property to solve for the A sub L terms. Here's how we do it. We multiply both sides of this equation by a different Legendre polynomial that we'll call P sub L prime. Then we'll multiply by sine theta and integrate both sides from theta equals 0 to pi. Okay, so here it is. We take this equation here, we multiply by PL prime, we multiply by sine theta d theta, and then we integrate. And here's what you get. It looks messy. Okay, now you can see the P sub L prime term on the left-hand side, the P sub L prime term on the right-hand side, and then there's a sine theta d theta, because for this coordinate system, when we do an integral, we have to multiply by that sine theta in order for things to work out in a normalized way. So the order of the summation and the integral are independent, and what I've done is I've pulled outside the integral any of the terms that don't have any theta dependence. So the A sub L and the R sub L don't have any theta dependence. They came outside the integral. Now, orthogonality of the Legendre polynomials means this. Unless L equals L prime, these integrals will be 0. Always. So all of the terms in this summation, an infinite number of terms, of those terms, the only one that survives is where L prime is equal to L. And for that term, you can show very easily that this integral gives the quantity 2 divided by 2L plus 1. All right, and this, here's another mistake, I'm sorry. This should say 2 over 2L plus 1 if L equals L prime. So all I have to do with this equation, and I'll do it at the top of the next slide, is replace the integral with 2 over 2L plus 1, and then get rid of the summation, because only one of those terms survives. So here's what we get. A sub L, R to the L, over 2 times 2 over 2L plus 1 equals the integral that's on the right-hand side. Okay? So, solving this for A sub L gives a very simple looking expression, so that if I now know the function V naught of theta that describes the potential on the surface of the sphere, I can plug it into this integral and I can crank out the value of each term. A sub 0, A sub 1, A sub 2, and so on. Right? I can find the coefficient A sub L for any L value, in principle. So I'm almost there. The only thing left to do is to find the B sub L coefficients that appeared in the solution for the potential outside the sphere. And the way we get this easily is by doing something I alluded to a few minutes ago. We take V in and V out, plug in little r equals big R and then match them at the boundary, because the potential should be continuous at the boundary. So that makes a very simple prospect of finding the B sub L coefficients if I already know the A sub L coefficients. So I just take those two expressions. On the left, that's V in, but I've substituted in little r equals big R. On the right, I have V out. I substituted little r equals big R. And then what I have with this infinite sum is the only way that the two sums can be equal is if they're equal term by term. Each term in the sum has to be the same. Again, this is a property of the orthogonality of the Legendre polynomials. So if that's the case, then A sub L, r to the L, has to equal B sub L over r to the L plus 1. And I'm going to solve now for B sub L. What I get is B sub L is A sub L, capital R, to the 2L plus 1. All right, big picture then. We've solved the problem. Why have we solved the problem? We know the general form of the solution. The only undetermined constants in the solution were the A sub L and the B sub L terms, and now we know how to find them. The equation up here gives me the A sub L's, and then the last equation gives me the relationship between the B sub L's and the A sub L's. So if I find the A sub L's, I automatically get the B sub L's from this last equation. I know that's a lot. We'll flesh this out by working on some examples in class, and the homework will also give you practice solving this kind of boundary value problem. I'll see you in class.